Hello, thank you. I'm happy to be here to present my work that I have been focusing on these last years, that is on use of different computational and theoretical techniques to understand what is the behavior of magnetic nanoparticles for some applications, especially hypothermia, and trying to develop predictions helping to further the experiments. The summary of my work is I have been focusing on understanding the process that if you have a set of magnetic nanoparticles and you apply an AC field, those particles will release energy and increase the temperature of the sample. So what I do is I simulate hysteresis loops because there is a correlation between the hysteresis area and the temperature increase. And I also try to study what is the evolution of the particles within the viscous environment, because that will affect the performance of those. And the context is that currently, as I show there is the view in this field that you apply an AC field and there is a heating, and that's the characterization of the system. But that's not true, because we know there are some experiments showing damage on cells without global temperature, so that is a problem to characterize. How do you know if the only technique we apply to characterize is the increase in global temperature? How can we know what is going on at the local level? There are some experiments showing that there is a long time scale reorientation, so how to take this into account. There are also the possibility of other heating mechanisms, but I will not describe those. So the outline, I will describe briefly some biomedical applications that I motivated this work, some basics of nanomagnetism, material properties, that is something we are familiar with, but especially the magnetization dynamics, because that is the key particularity of nanomagnetism for applications. I will summarize the computational tools I mainly use that are based on macrospin model and micromagnetic descriptions. There are also some Brownian dynamics, but I will not deal with those. And if I have time enough, I will get into some details. So the motivation for this started with magnetic fluid hypothermia. It was described already yesterday that this is an alternative cancer treatment technique that is based on the fact that the tumor cells are more sensitive to a temperature increase than the normal ones. And since the particles release energy when you apply an AC field, you could think that, okay, let's deliver the particles to the tumor area, because we can apply an external field that we know is safe for the body and try to hit the local area without secondary effects. There is something that is very interesting, that is the magnetogenetics, that is the possibility to control the behavior of cells activating some thermosensitive ion channels that would be delivering magnetic nanoparticles to some cells overexpressing this type of channels. The success of this is mixed. On the one hand, it's been almost 10 years since the hypothermia has been approved for the treatment of one cancer that is called glioblastoma. But that is because the overall survival after recidival of the cancer is 12 months. So it was a success, this hypothermia, because almost double the survival, but it's not that big. It's good in the sense that it avoids secondary effects. So for the patient, it's better, but it's not that good. And magnetogenetics shows very fancy results. The control of freely moving mice can be shown. But of course, there are some other applications like rewarming of cryopreserved biospecimens, because that is something that is for when you need to make a transplant. You cold the sample, but to warm it under room temperature is complicated if you are from the inside. So that limits the temperature that you can cool the sample, so that in average you cannot be more than 4 hours distance. And so if you inject magnetic nanoparticles homogeneously distributed within those, it would be a way to control the homogeneous heating of the sample, but still the success is very limited. I mean, it's very promising, but you don't see magnetic hypothermia working in the hospital. Only if you go to Germany, some countries in the north, but it's something, why? Because there are multiple problems. Most of them are not related to what I do, that is just material science, it's bio. The delivery of the particles is, I guess, the biggest one, but there are some problems. But for me, from the physics point of view, the problem is that there are no models able to describe what happens to nanoparticles if you have them in a viscous media. It's complicated to have accurate models for the heat dissipation, but it's even more complicated to describe the colloidal evolution, because the time scales for heat dissipation, they reach nanoseconds, and the colloidal evolution during a treatment would last like 20 minutes. So it's very complicated to reach the material, the different dimensions, but the time scales are the key. So simplest, nanomagnetism, if you have at least one scale that is in the nanometer. From the material properties, the key difference is that you go from the dominancy of the long-range magnetostatics to short-range exchange. That is in general. We will see later on that there is something more, that is the anisotropy is the key, as Victor described it earlier on. But first, this is the main effect. Of course, for applications, the role of the surface is very important as well. It was mentioned in a previous talk how the ratio between the contribution of the surface increases dramatically with lowering the particle size. But what I am more interested on is on the magnetization dynamics, because if we want to release energy, we need some dynamics, and the dynamics of the nanoscale magnets are really different. If you think on bulk magnetism, temperature gives you, well, just a decrease in the magnetic moment. And that is the same effect that you get in nano. You will get a decrease in the net magnetic moment. But the key is that in this nano, there is some, the magnetic moment in itself can fluctuate internally. What is the meaning of this? The meaning of this is that what we call that a magnet has a north and south pole. That makes sense if we think in the Earth. The north and south poles of Earth are, well, it's fixed for us in our time scales. If you go to something smaller that is bits, that is not like that, because we know the information in our hard disks or in the cloud that is essentially hard disks is stable in average about 10 to 15 years. But if you go to nano, we see that the stability of the magnetic moments decreases rapidly. Just lowering a few nanometers the size lowers the stability from minutes to even nanoseconds time scales. And what is important here is that there is a critical role of the magnetic anisotropy. In nano, magnetic anisotropy is the key for everything. You can have a very good particle with a large magnetic moment that if the moment is not coupled to the lattice, there will be no effect. The magnetic moment will reorient under the field, but the particle will not feel it. The anisotropy is what links the magnetic moment to the lattice, what defines our north and south poles. There are different contributions, crystalline, shape, surface, but in the simplest description, it is what makes our magnet to have the north and south poles. But this is working only for the ideal T equals 0 case, or equivalent to the infinite anisotropy. Temperature defines some probability of a spontaneous reversal of the magnetization. Is the anisotropy together with the particle size what defines how stable is our magnetic moment. Anisotropy is the key for everything. That is the message that I want to say. And if you're thinking on a magnetic nanoparticle and you apply a field, the magnetic moment will try to follow the field. Depending on how strong is the magnetization coupled to the lattice, that there will be a physical reorientation or not. If we are applying an AC field, it may happen that we reverse the field before there is physical reorientation. So we need to take into account the time scales for relaxation and for rotation of the particles. So let's go back. This is the problem that we want to study. What is the behavior of the magnetic nanoparticles in a viscous media and under AC fields? We can think that the particle rotates or that we promote the inner magnetization reversal. But this picture that we had in mind, comparison of time scales, doesn't work anymore, because if we apply an AC field, if we apply a field, we can promote field-induced switching, so that is nanoseconds time scales. So in general, hypothermia and these magnetomechanical actuations have been considered that if you are on high frequencies, you have only internal magnetization dynamics. If you are in low frequencies, you allow the particles to rotate under the AC fields. But we know this is not true. This only happens in a very narrow range of field amplitudes. If you go to something like typical hypothermia experiments with iron oxides, field amplitudes of 200 to 300 Ørsted and a few hundred kilohertz, what you will have is a combination of switching and rotation. And the problem is that there is no analytical way of solving this, because you can define the equations for dynamical reorientation, but as soon as you get a critical event, that is where dissipation occurs mostly, you cannot predict the behavior. So to deal with this, I have been working on different, we need to use different computational approaches, because I will not get to this, but the problem with the magnetic nanoparticles is that you have a random contribution of orientations, interactions, dispersion in properties, a lot. So, but bigger than that is the influence of what is what you want to do, what is the time scale, and how to study those properties. So we need to deal from quasi-equilibrium properties, that is like magnetocalorics, if we want, for example, to use standard zero field cool techniques. We need to go to seconds or milliseconds time scales if we want to understand the colloidal evolution over time. Of course, for hypothermia, we need to go to hundreds of kilohertz. And we may even go into the pico to femtoseconds regime that is almost the ultra-fast dynamics. We don't need to do that for hypothermia, but the integration times that we need to use sometimes reach those. So the amount reaching, if we need to consider nanoseconds at least, but picoseconds time scale to simulate a process of heating, how can we reach the biomedical process of minutes? Well, we need to make some approximations. Regarding this, I mentioned this about the dimensionality, but if we want to study large systems, micron-sized systems, we cannot use most of the techniques. We can only do energy minimization mostly with micromagnetics. We can simulate multi-layers, we can simulate nanowires, but we are limited to very specific conditions. If we want to study magnetic nanoparticles, we can study those as a whole. We need to make some assumptions like macro spin approximation, that there is a coherent rotation of the inner atomic magnetic moments, or we can try to characterize single particle properties. We have different techniques from Monte Carlo to Landau, that is mostly equilibrium or quasi-equilibrium. Landau-Lipschitz-Gilbert equations, that is the dynamical movement. We can use Brownian dynamics or molecular dynamics, but that only works for the rigid dipole assumption, so it's useless for what we do. So it's complicated to define what to use. For the single particle properties, we have more tools to use, but we are limited. If we want to make an application that requires millions of particles, studying one particle is limited as well. Here, just 1 minute, I'm showing some results that we can do simulations of single particle properties, assembly of particles, and see how those dynamically correspond with experiment. All the results are, all the papers I'm showing here are related to experiments, either to predict or to understand how those systems of particles evolve for hypothermia. We can try to understand this collaboration was motivated because delivering magnetic nanoparticles of cobalt ferrite within cells or iron oxide within cells of the even slightly bigger particle size for the iron oxides, it was observed the spontaneous formation of chains, and even that those for the cobalt ferrites, but not for the iron oxides. So we developed some model to explain this based on the likelihood of agglomeration depending on the stability of the magnetization, but the details are there. And this is just to show that I can deal with very specific samples, but I am limited to sizes about 25, 30 nanometers and above. In those cases, I can do, for example, core shell structures or with voids in the interface. In this case, it was studying soft shell with a not that hard, but hard core and a paramagnetic interlayer. And I can vary systematically the total particle size, the aspect ratio, the role of the crystallinity of the different phases. If I go to one particle, the details are much bigger, of course. And with that, it's it. I thank you.
Thank you. Questions? Preguntas, comentarios? Sí.
David, voy a hablarte en castellano.
Sí.
Interesante. Tienes las técnicas de Monte Carlo, de Landau. Una pregunta. Esto es importante para los experimentales. La alejación de Nel, comprendido. ¿Y tienes simulación de la de Brown?
Sí.
¿O eso? Sí.
Están acopladas. Sí. Hay un código a mayores. Esto, para describir esto, botei como 6 meses intentando facer unha aproximación analítica en donde conectaba unha ecuación dinámica de rotación coa inversión. Intentaba facer un modelo analítico porque sería moito maior, claro. E é imposible. Entonces o que fixemos foi un código incluyendo Brown e Nel, pero sin difusión. Con difusión estamos traballando ahora. Sí. Claro, pero sí, hay... Eso sí que es súper costosa, esa simulación.
Muy bien. Una pregunta más y vamos a cambiar un cable.
David, nice talk. So you mentioned a couple of times about that you're interested in viscous media. How does viscosity come into play in your calculations? How do you introduce viscosity?
I do some simulations on Brownian dynamics. The problem is that I do the simulations, the Brownian dynamics or molecular dynamics, you assume rigid dipole. So I do some simulations considering the viscosity of the samples, but actually I don't think that is that useful. That's why I didn't have, that's why I came with this approach. I think it's more useful to know what happens in the sample to use characteristic time scales than to use the molecular or Brownian dynamics, because those would only work if you are either at 0 Kelvin or if you have very large anisotropy. But I am working on including the dynamics of the magnetization on a standard molecular dynamics code, but it's taking time.
Nice, thanks.
Thank you.